Maintaining a safe working environment includes designing and maintaining a safe electrical environment. Electrical codes, rules, and regulations are used to create a safe electrical environment. High voltages used in commercial and industrial electrical systems can be dangerous, even deadly. Electrical automation systems use control transformers to step down high voltages to create a safer electrical environment. Commercial and industrial motors are controlled with motor starters. Coils are used to control the operation of the starter. In control systems, lower voltages are used to create a safer electrical environment. Transformers typically change a high voltage into a lower voltage. In the example shown, the transformer is used to produce 24 volts. 24 volts is used to control the motor starter. Transformers that are used to produce a lower control voltage in electrical and automation systems are called control transformers. The main purpose of a control transformer is to create a safer electrical environment. Control transformers are considered step-down transformers, that is, it produces a lower voltage. The voltage that is supplied to the transformer is called the primary voltage. The voltage that the transformer produces is called the secondary voltage. The control transformer shown here is supplied with 460 volts and produces 24 volts. The schematic symbol for a transformer identifies the primary and secondary connections. The 460 volt primary connections are identified with H1 and H2. The 24 volt secondary connections are identified with X1 and X2. The electrical specifications are identified on the transformer: the primary voltage, the secondary voltage, and the wattage. The wattage is listed as VA. The transformer wattage is used to determine the overcurrent protection. Notice that overcurrent protection can be calculated from the primary or secondary voltage. Overcurrent conditions can damage or destroy a transformer. The two most prevalent voltage systems used in industry are 230 volts and 460 volts. In order for control transformers to be more versatile, manufacturers produce dual voltage transformers. A dual voltage control transformer can be wired to accept either 230 volts or 460 volts for the primary voltage. Even though various dual voltage transformers are available, dual voltage transformers that can operate on either 230 volts or 460 volts are the most common. To understand the basics of a dual voltage transformer, let's review some circuit fundamentals using Ohm's law. In the example, a 120 volt lamp has a resistance of 120 ohms. When the lamp is connected to 120 volts, 1 amp of current flows. If two of the lamps are connected in series and then connected to a 240 volt source, 120 volts is dropped across each lamp. When the lamps are connected in series, both will have the correct voltage. Notice in the example how the lamps must be connected to operate properly. The lamps must be placed in parallel to operate on 120 volts. The lamps must be placed in series to operate on 240 volts. Just as with these lamps, series and parallel connections of transformer windings will allow the transformer to operate on one of two voltages. Control transformers may be designed for single primary voltage and a single secondary voltage. This type of transformer has only two connection terminals for the primary voltage and two connections for the secondary voltage. Notice the schematic symbol for a control transformer in that the primary voltage connections are identified with the letter H, and that the secondary voltage connections are identified with the letter X. The transformer specifications are identified on the transformer. Let's examine how the primary windings can be constructed to accept either 230 volts or 460 volts. In this example, the primary winding is designed for 460 volts. When primary connections H1 and H2 receive 460 volts, it produces 24 volts. Transformers that are constructed with the primary winding split are capable of operating on 230 volts or 460 volts. A dual voltage control transformer has the primary winding split into two equal parts. This allows the windings to be placed in parallel or series in order to accept either 230 volts or 460 volts. A dual voltage transformer splits the primary winding into two equal windings. Notice that the primary voltage connection points are identified with the letter H. The control transformer shown here has a 460 volt primary winding. The 460 volt primary winding of a dual voltage transformer is split so that each half will operate on 230 volts. The two windings can be connected in parallel to operate on 230 volts, or in series to operate on 460 volts. Let's examine the transformer connections for each. Primary connections on a transformer are identified with the letter H. When the primary winding is split, the result is 4 connections. The 4 connections are identified as H1, H2, H3 and H4. H1 and H2 are connected to one winding and H3 and H4 are connected to the other winding. When the primary winding is split, each winding operates on 230 volts. For the transformer to operate on 460 volts, the two primary windings must be connected in series. A series winding connection is accomplished by connecting H2 and H3. 460 volts is then supplied to the outside winding connections H1 and H4. For the transformer to operate on 230 volts, each winding must be supplied with 230 volts. 230 volts is supplied to one winding with connections to H1 and H2. 230 volts is supplied to the other winding with connections to H3 and H4. The two windings are placed in parallel and connected to 230 volts. Let's examine how the internal primary windings are arranged for terminal connection convenience. Control transformers with dual voltage primary windings have 4 terminal connections. Let's examine the winding connections for 230 volts. The transformer shown is made for a primary voltage of either 230 or 460 volts. Transformer references may identify the 230 volt connection as the low voltage. Since each winding must receive 230 volts, the two windings are placed in parallel. Notice that H1 and H3 are connected to a line and H2 and H4 are connected to another line. Each winding is supplied with 230 volts. For wiring connection convenience, manufacturers typically move the H2 connection and the H3 connections to opposite sides. This allows for adjacent connections for H1 and H3 and adjacent connections for H2 and H4. Control transformer field wiring includes installing the transformer connections for the primary windings and power connections. Next, let's examine the windings and the winding connections for 460 volts. The transformer shown is made for a primary voltage of either 230 or 460 volts. Transformer references may identify the 460 volt connection as the high voltage. Since each winding is rated for 230 volts, the two windings must be placed in series in order to split the incoming 460 volts into two equal voltages. The windings are placed in series by connecting H2 and H3. The line voltages are then connected to H1 and H4. Since H2 and H3 are connected together, it makes no difference that H2 and H3 are on opposite sides. Control transformer field wiring includes installing the transformer connections for the primary windings and power connections. A transformer wiring diagram identifies connections for a primary voltage of 230 volts, a primary voltage of 460 volts, and the secondary voltage connections. A typical transformer is supplied with metal connection jumpers. If not supplied with the transformer, it may be necessary to make the jumpers. The jumpers are used to make connections for either a 230 volt primary or a 460 volt primary. Two jumpers are used when the transformer primary is supplied with 230 volts. One jumper connects H1 and H3. The other jumper connects H2 and H4. 230 volts is then supplied to H1 and H4. Only a single jumper is used when the transformer primary is supplied with 460 volts. A single jumper connects H2 and H3. 460 volts is then supplied to H1 and H4. The transformer supply voltage must be identified and the corresponding jumpers installed for correct operation. The transformer can be damaged or destroyed if wired incorrectly. The secondary winding of a control transformer can be split. When the secondary winding is split, the transformer has the capability of producing a low voltage or a high voltage. The transformer shown here can produce either 115 volts or 230 volts. The secondary winding connections are similar to the primary winding connections in that parallel windings are associated with the low voltage and series windings are associated with the higher voltage. In the transformer shown here, the two secondary windings are placed in parallel. When X1 and X3 are connected, and X2 and X4 are connected, the transformer produces 115 volts. In the transformer shown here, the two secondary windings are placed in series. When X2 and X3 are connected, the transformer produces 230 volts. It is important to provide overcurrent protection for a transformer. Overcurrent can damage or destroy a transformer. Overcurrent can be provided for either the primary winding or the secondary winding. Transformer overcurrent protection is typically provided for only one side. Typical control transformer overcurrent protection is provided on the secondary side. Since breakers and fuses are rated in current, the transformer wattage and voltage are used to calculate the overcurrent value. Overcurrent protection for the primary side of the transformer is calculated using the wattage and the primary voltage. Overcurrent protection for the secondary side of the transformer is calculated using the wattage and the secondary voltage. Dual voltage control transformers are very common in electrical and automation systems. They are designed to accept and produce different voltages. Although the dual voltage transformers shown in this video are common, a wide variety of control transformers exists. Always refer to the specifications of the control transformer to verify all of the connections.